Well, thank you very much, Andrea, for the introduction, and welcome to the Swine Leman conference. It's my honor to be here presenting to you a mainly nutrition topic to a traditional veterinary community. One of the items that, or the first item where my advisor introduced me when I was graduating and doing my PhD, he mentioned, we have had Pedro here at the University of Illinois for quite some time now. He's been trained to think not as a veterinarian anymore, but as a nutritionist, and now finally he has the mind of a nutritionist. So, but today I will argue that we need to work on these type of events like we are going to have today, where production may be meeting and nutrition may be meeting health or other aspects that are not directly on caloric uptake by the animals. With that, I want to make an overview of enzymes, mainly basically on carbohydrates enzymes. And the first step to talk about when we talk about enzymes is to understand that animals, like us, nutrients need to be degraded and able to be absorbable. And we do that mainly by grinding feed, but even though feed is ground and animals can masticate and decrease the particle size, something has to further be broken down for it to be digestible and absorbable. And the way that once we've ground the feed and once the animal has masticated and broken that down is by use of enzymes. So what are the enzymes and how do they work? How do they break down the feed? Well, enzymes are no more than proteins that modify the activation energy to accelerate chemical reactions or catalyze chemical reactions. And this one goes back to our old biochemistry teachings where we say the reason why this table right now is not combusting, it's not burning, is because the energy that would take to burn these to get the reaction going is far away from the initial level. So something needs to give energy for this wood to be burned. Similar happens to feed when it's absorbed in the GI tract of the pig. So, for example, starch, in able to start breaking down starch within the GI tract, starch will be at one level of energy. That energy needs to be increased where the reaction can take place. So enzymes, what they do is actually decrease the energy that will be required to activate or to get that reaction going, and this is called activation energy. So the first concept is enzymes are necessary for digestion. Things, fiber corn can sit in the field and can be degraded for many, many years without the use of enzyme. It would take so long that life would not be able to be. So enzymes then help to decrease the energy activation and degrade the, for example, starch in corn into a fast way that can be able for the animal to be used. The next thing to remember is that no matter the reaction occurs with an enzyme or without the enzyme, the final product is the same. So, and this goes to the laws of energetics. No matter what path that energy takes, the end product will be the same. So with enzyme or without enzyme, and the product will still be the same. And we'll keep this in mind as we talk today. The second item to keep in mind as we talk about enzymes is the specificity or the key log activity of enzymes. In this diagram, we have the enzyme in gray color and a substrate, the initial substrate in yellow color. And the active size of the enzyme, and that active size and the product are very specific to each other. So without this specificity or without this active site matching the substrate, the enzyme would not work. The activity of the enzyme would decrease. And this is a second concept to keep really in mind as we talk about today about enzymes. Finally, well, the product match with enzyme, the reaction is catalyzed, and we can get the broken down product. Usually, a lot of times, the product itself can inhibit the enzyme in different ways, or the enzyme will require factors or cofactors to work properly. In the GI tract of pigs and in nature, there are multiple enzymes to do all biological reactions. And this is a very short list to point two items. Some enzymes are available in the animal. Some enzymes are not available in the animal, but are available in nature. So the ones that are not available in the animal are those highlighted or with the underline. So proteases, for example, they are used to degrade pepsin, trypsin, chymotrypsin. Proteases are degraded by pepsin, trypsin, chymotrypsin, and carboxypeptidase that are secreted in the GI tract of pigs. That's how proteins are digested. Other, like fungi, can secrete another protein called keratinase that degrade keratin. It's a protein that animals will not be able to degrade. However, fungi in the environment are able to degrade keratin. Carbohydrates are amylase and maltase, for example, are enzymes involved in the digestion of starch. Corn will be the high starch or a high starch ingredient. We'll see this in a minute. And are mainly degraded by amylase. Other carbohydrates are degraded by Xylanases or beta-glucanase, degrade other type of fibers, and the animals itself have not the capability to produce or secrete these enzymes. So in this case, for example, the animal is lacking one enzyme that will match one type of carbohydrate, and I'll go to the structure of that carbohydrate here in a minute. But keep in mind, the animals have some, but have no others. Lipase or fatty acids are digested by pancreatic lipase, and the animal has the ability to secrete and digest fat. Other esterases like ferulic acid esterase and silane esterase are also necessary for degradation of fiber. Actually are not secreted by the animal, and I should have underlined this, but they are not secreted by the animal, but can found in other products. And I'll tell you in a minute why these are important. Finally, the other type of enzymes that we can find on the groups will be phosphatase. For example, alkaline phosphatase is an enzyme secreted in the gut lining of pigs. And phytase. Actually, pigs have the ability to some extent, degrade or have enzymes capable of degrading phytic acid. It's just that the phytic acid sometimes is not available to be degraded within the pH and the conditions that are in the GI tract. So that's the matter or the concept on the enzymes. And enzymes catalyze this degradation of products, and feed ingredients of high concentration or fiber cannot be completely degrade. Here on the y-axis we have apparent total tract digestibility of dry matter. So we take feed the animals, collect the feces, and analyze for the complete digestibility of dry matter. And we observe that, for example, corn, the value is much higher than, for example, corn DDGS. So pigs cannot digest all the nutrients or everything that is within corn. And not only within the ingredient, but among ingredients, part of that ability to decrease the digestibility is the type of nutrient that is contained in that grain. For example, rice and corn contain a high concentration of starch, and pigs secrete enzymes that are able to degrade starch. Therefore, digestibility of dry matter or digestibility of starch is high. However, the animal, as I mentioned, does not have the capacity to secrete enzymes that digest fiber or total dietary fiber, and therefore the digestibility of fiber is less, and therefore the digestibility of dry matter of corn DDGS, for example, is less than corn. Not only this digestibility varies among ingredients, but also here is an example that within one ingredient the animal is not able to digest and absorb all the nutrients within that ingredient. Here, for example, we have corn, apparent total tract digestibility of 5 different sources of corn, and there are differences in the digestibility of dry matter among these sources of corn. Not only in the digestibility of dry matter, but nitrogen, and even have greater differences in the digestibility of phosphorus. So the other part is that the grain, even though is all corn, there are differences in the digestibility within the grain. Part of those digestibility can be explained by the concentration of the dietary fiber. On the y-axis, on the x-axis, we have the concentration of neutral detergent fiber, and on the y-axis we have the digestibility coefficient of the same 5 sources of corn that I mentioned before. And you can see a trend or a decrease of the digestibility of dry matter as the concentration of NDF increases within the grain. Therefore, big part of why between ingredients and within an ingredient the digestibility is less is because dietary fiber. Or other components for what the animal is not ready to digest. Exogenous enzymes are extracted from microorganisms, prepared industrially, and being able to help us to degrade fiber or phytase or other products or within feed. A little bit of numbers. In the global feed enzyme market for 2011 was estimated about $550 million, saving the industry very, very large amount of money. Up to today, the main enzymes, the most well-known and used enzymes in animal and monogastric diets are phytase, followed by non-starch polysaccharides or fiber-degraded enzymes. And among these phytase are enzymes that degrade or they are able to release phosphorus from phytic acid. In corn, the majority of phosphorus, about approximately 60% in the cereal grains, is contained in this structure called phytate. And phytate is also called myo-inositol when it has all six phosphorus or all 6 substitutions, then we call it inositol hexaphosphate. Pigs cannot digest phytate to a very efficient level, and therefore the use of phytase, the enzyme, can be added to aid the digestibility of phytic acid. One important initial driver for the use of phytase in the diets for pigs was exactly phosphorus. Nowadays, new applications are coming in, and later on, other presenters will have more data on that. But the initial intent was that by decreasing the amount or increasing the efficiency of utilization and digestion of phosphorus in pigs, then less phosphorus will go into the environment and decreasing pollution, environmental pollution. Now, not only phytase will release phosphorus, but it can release other nutrients within the structure. I was mentioning to you of the 6-ring structure of phytate, and phytate has all substitution of phosphorus. And in this case, when it has the substitution of phosphorus, within the phosphate groups, you can have cations that can be bound or tightly in relationship with the structure, decreasing or chelating and decreasing the digestibility or the availability of, for example, in this case, calcium for digestion and absorption. So therefore, when we destroy phytate, the phytate molecule, to some degree we're releasing not only phosphorus, but we can be releasing calcium, we can be releasing proteins, and we can even release starch and zinc. However, the release of these nutrients is not all linear, and it depends on how much chelation there is, the underlying product, and the activity of the enzyme. But today I will not focus anymore on Phytase more than just giving that introduction, because I want to have some time to talk about the more growing part of applications of enzymes on carbohydrates enzymes or enzymes able to degrade the fiber. If you look at the horse NRC, or if you look at the classification, it's very useful to use this picture, where we can see that plant carbohydrates can be classified as intracellular carbohydrates or cell wall carbohydrates, or from a nutritional standpoint into carbohydrates that can be digested and absorbed in the small intestine without the aid of other enzymes or microorganisms, and carbohydrates for which the animal do not have an inherent capacity to digest and absorb. In this case, these sections of carbohydrates are digested or are degraded in the large intestine by fermentation, and the product of those are absorbed and available for energy in the animal. So that it would be the classification based on nutritional impact of the carbohydrates. The majority of those fibers that we see in plants that in the raw materials that we feed to animals will come mainly in two carbohydrates, hemicellulose or cellulose. There is a structure or a chemical called lignin that is tightly associated, not a carbohydrate, but tightly associated to lignin and cellulose, and therefore we do consider that part of the fiber when the animal consumes fiber. And this is a brief diagram to demonstrate the relationship between these structures. If you were to look at fiber in the plant cell wall, the plant cell wall needs structure. It needs a way to hold the plant up, and the cell walls give part of that structure. How do I confer that? Well, let's think of the cellulose myofibrils as the beams that sustain the structure, and we can see that arabinoxylans would be the connections between those beams, and that holds the structure together. Usually, cellulose are packed into tight sheets like book sheets, and it's very insoluble because no water can get into the structure. However, within hemicellulose there are different structures, and the structure is more loose, therefore more degradable. So one way of thinking that is cellulose are traditionally less degradable than hemicellulose. Hemicellulose are, for example, in the case of corn fiber, mainly composed of a carbohydrate called arabinoxylans. And arabinoxylans are no more than xylose. These xylose all cling together with substitutions of arabinols. That's very simple why they are called arabinoxylans. Now, if you see that cellulose and arabinoxylans are bridged together or bound together by diferulic or ferulic acid phenolic compounds. And those are the ones making the gap between the two, or making the bridge between the two structures. And the concentration or the shape of these structures within the different grains is different. In this case, this is the total concentration of dietary fiber. Corn contains less fiber, for example, than DDGS. Wheat and corn may contain somewhat similar concentration of fiber. Always wheat contains some more, and barley contains more. But not matter much as the concentration itself of the fiber, but the structure of that fiber. And how does the animal react, or how does the animal handle that extra fiber? In this case, we have a ratio between soluble and insoluble dietary fiber. And I explain here in a minute. If you were to take these arabinoxylans that I explained you before from corn, and you put it in a solution, those arabinoxylans will not enter solution, will not dissolve. However, big part of the arabinoxylans within wheat or barley will enter solution. So immediately you can see that there are differences in the type of fiber among feed ingredients. And one of those differences is or a simple measurement of that difference is solubility. However, in a minute I will mention that that solubility is not the full story. And it's not the full story, and it depends also on how the enzyme will interact with the arabinoxylans. In this case here, we have a classification of Xylanases, or the enzyme that degrade arabinoxylans. Remember that arabinoxylans are the main constituents of hemicellulose in corn fiber. So there are enzymes able to break down the arabinose residue. There are enzymes that are more specialized to break down in the middle, or endo-Xylanases, or Xylanases that could degrade fiber from the end, or exo-Xylanases. And the enzymes get more specialized at breaking down, or more efficient to breaking down fiber at specific sites of the structure. And that's what I want you to remember, that specificity of the substrate matters for the enzymes. And if you're looking for more information or what is the classification of the enzymes, the carbohydrate activity website, or enzymes website, is where they are all molecularly classified. Well, those are how Xylanases are, but what has been the activity of these enzymes, for example, in the diet for pigs? And here is a summary, a table summarizing the type of distillers grains that animals were fed, either wheat, corn, DDGS, the enzyme type that was used, and a percent or a type of response. I'll guide you here a little bit slower, but the main message that I want you to get from here is that that response is variable. So in this case, for example, within wheat, we're feeding a Xylanase, obtain a 6% improvement in digestibility of protein, and a 12% improvement in digestibility of gross energy. However, in another enzyme, in another situation, where they were feeding, for example, corn DDGS in a combination with Phytase, they observed no response in growth performance. Or in this other trial, where they were using Xylanase in combination with other pectinases, they only observed 2% in digestibility of dry matter, or on average daily gain. Therefore, up to now, within pigs, the effect of Xylanases enzymes has been variable. So what factors are making this digestibility or this effect of the enzyme variable? Well, I can think of, for example, how much substrate is available. Remember, I told you that the enzymes are specific to the substrate. If it's not there, the enzyme is not going to work. The second one is the structure of that. There can be arabinoxylans, but arabinoxylans for corn are different from arabinoxylans in wheat. And the solubility of the substrate. There are interaction among nutrients, and as I mentioned before, for example, in the case of Phytase, Phytase may not be releasing only phosphorus, but it can be releasing starch and other nutrients. A thermal stability of the enzyme, or interaction among the enzymes. The activity of the enzymes, for example, seems to be greater the lower the energy of the diet. And if you think that in many cases lower energy diets will contain higher level of dietary fiber, therefore that will drive a greater impact of that enzyme. Not only does the concentration of fiber, for example, within samples of DDGs varies, but that digestibility changes too. So if we put that in combination, what we will calculate the amount of digestible fiber or the amount of fiber that can be degraded by the animal itself. And the contrary of that will be the fiber that will need to help the animal degrade it. For example, in this case, we have the amount of fiber being able to degrade by the enzyme. So you can think of two options. The enzyme may have greater activity, the lower digestible, because they have more room to work. However, you can think also that the structure of this fiber can be in a way that is more available to the enzyme to be degraded. Therefore, nutrient release within the fiber can be explained, or within enzymes can be explained by using of in vitro procedures or animal procedures too. And we need to keep in mind, as we study more enzymes, that the effect of the animal may be dependent on other factors, not only the energetic release. In this case, was an experiment done in our laboratory where animals were fed a controlled corn soybean meal diet. A diet with wheat straw, with DDGS, and soybean pulse. The reason we select these ingredients is because all these three ingredients contain high level of dietary fiber and high level of insoluble dietary fiber. We fed all animals to the same level of total dietary fiber. So the animals were consuming all insoluble fibers and all the same level of that fiber. And in spite of these differences, we were able to see that, for example, the number of goblet cells, the cells that are in charge of secreting mucin, differs among the different group of pigs. So not only the type of fiber, the amount of fiber makes a difference to the animal, but the type of fiber that the animals are fed. One implication, for example, in this case, is that in the case where animals had more mucin and had to liberate more mucin, then they will have a greater requirement of the amino acid threonine. And because we have already seen in the latest NRCs that fiber can drive threonine requirements because of secretion of mucin. But what type of fiber? We see that not all fibers are the same. So are Xylanases partially working on a effect that is beyond just the energetic effect? Is something that we need to still work on. So therefore, in summary, the efficiency of feed utilization can be increased with the addition of these carbohydrates enzymes or exogenous enzymes. Carbohydrates degrade non-starch polysaccharides, and phytase degrade phytic acids and increase the digestibility of phosphorus, but also other nutrients. The effect varies according to dietary factors, for example, substrate availability, how that substrate is in the structure, and condition in the digestive tract of pigs that may change with the addition of fiber.